Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Jacobians. Please be an active learner as you listen to this video. By way of introduction to the topic of change of variables in multiple integration. In one-dimensional calculus, we often use a change of variable, a substitution, to simplify an integral. By reversing the roles of x and u, we can write the substitution rule this way. So the definite integral from a to b of f of x dx was the definite integral from c to d of f of g of u, g prime of u, du. This was the substitution, where x is equal to g of u, and a equal g of c, and b equal g of d. Now another way of writing this formula is this way, where we're calling this x of u, and this dx du, and you see those will symbolically anyway look like they cancel out, and you get the dx back again. Also, we saw a change of variables could be useful in double integrals. And one example of that was when we converted to polar coordinates. You see, we said that x was r cosine theta and y was r sine theta. And so the change of variables that we learned was this one. The double integral over the region r of f of xy dA was equal to the double integral over S. Now S was the region in the r theta plane that corresponded to the region r in the xy plane. And we made the substitution f of r cosine theta, r sine theta, but then dA became r dr d theta. So we had this factor of r that emerged here, and if you remember, we used geometrical means to determine that that should be r. Also remember, we did a change of variables using spherical coordinates in triple integrals. Recall that the triple integral over a box E of f of x, y, z dv ended up being this triple integral here, this iterated integral, and this was f of rho sine phi cosine theta, rho sine phi sine theta, and rho cosine phi. And dv became rho squared sine phi d rho d phi d theta. And remember that this factor rho squared sine phi came from geometrical considerations associated with the change of variable. So more generally, we consider a change of variable that's given by a transformation t from the uv plane to the xy plane. So t of uv is equal to xy, where x and y are related to u and v by these equations. X is equal to g of uv, y is equal to h of uv. Or we sometimes would write x equal x of uv and y equal y of uv. We're usually going to assume that t is a C1, that means continuous first partial derivative transformations, which means that g and h have continuous first partial order derivatives. I guess I said that already. So a transformation t is really just a function whose domain and range are both subsets of R2, the two-dimensional plane. If t of u1, v1 is equal to x1, y1, then the point x1, y1 is called the image of the point u1, v1. If no two points have the same image, t is called 1-to-1. And the figure down here shows the effect of the transformation t on a region S in the uv plane. So we have S over here, t takes us over to here, and this is where the points go, and the inverse will go the other way. if there is an inverse. And if t is a one-to-one transformation, then there is an inverse, t inverse, from the xy plane to the uv plane, and it may be possible then to solve those equations. So u is equal to capital G of xy, and v is equal to capital H of xy. And in practice, we will in fact do this solution. So let's practice this just a little bit with an example. A transformation is defined by the equations x is equal to u squared minus v squared, and y is equal to 2uv. We're to find the image of the square, and this is in the uv plane, where u is less than or equal to 1 and v is less than or equal to 1, and both of those are also bigger than 0. So it is the set of uv in the R2, the set of uv, where u is between 0 and 1 inclusive, and v is between 0 and 1 inclusive. You know what to do. Let's see how you did. So recall our transformation is this, and we're to find the image of this square uv in the uv plane. So this is the square we're looking at, and we're going to look at each side. So let's look at S1 first, which is down here. So the first side, S1, is given by v equals 0, and u runs from 0 to 1. So from these equations up here, we have that x is equal to u squared, and y is equal to 0. So when u runs from 0 to 1, so does x. So you see this S1 ends up being this little piece over here. And now what we're going to do is the second side. The second side is S2. This is S2 here. So u is equal to 1 and v runs from 0 to 1. Now if we put u equal 1 in the equation, we get up here in this equation, we get that x is equal to 1 minus v squared, and y is equal to 2v. Now, if we solve this for v, then we say v is equal to y over 2, so x is equal to 1 minus y squared over 4, and x runs from 0 to 1, so we have this expression here. So now, S1 was this one, S2 was this one. Now in a similar fashion, when we work through this, we can find that x equal y squared over 4 minus 1 when x runs from minus 1 to 0, and that is what happens when you do S3. Now S3, you see you're going from the top to the bottom, and then what you have then is S4 is going to then be, this will be, changing this. So what we end up having is this square is mapped into this parabolic region. And again, here's another picture of it. This square is mapped to this parabolic region. And so here was 1, 2, 3, and 4. Now let's see how a change of variables affects a double integral. We start with a small rectangle S in the UV plane, whose lower left-hand corner is U0, V0. And its dimensions are side delta U and delta V. Here's the picture. The image of S in the XY plane is a region R, one of whose boundary points is x0, y0 is t of u0, v0. This vector, the vector r of u, v, equal g in the I direction and h in the j direction. Those are functions of u and v is the position vector of the image of the point uv, where we have it up here. the equation of the lower side of S has V0 fixed, and so we have an R of U with V0 fixed. The tangent vector at x0, y0 is then the image curve, and so that is R partial U, and we have V0 fixed, and we can take that at again V0 is fixed, and this could be written as this is the partial of x with respect to u in the I direction and the partial of y with respect to u in the j direction. Similarly, the tangent vector at x0, y0 of the image curve at the left side is going to be given by the partial of x with respect to v in the I direction and the partial of y with respect to v in the j direction. Now we can approximate r then by a parallelogram where we have two side vectors, and the side vectors are going to be a and b, shown here. And those are going to be approximations. I'll show you a picture of that in a minute. But recognizing that this partial is the limit, we know that we have the following relationships. That r at u0 plus delta u, fixed at v0, minus r at u0 v0 is approximately equal to delta u times ru. And similarly, r at u0, and this is v plus delta v0 plus delta v, is minus r of u0 v0 is approximately delta v times r partial with respect to v, delta v times r partial with respect to v. So what we're doing, here's the a and b I promised that I would show you. This means that we can approximate r by a parallelogram determined by this vector and this vector. I'm going to show you a picture of that in just a minute. So we can approximate the area by the area of this parallelogram. But we learned what the area of this parallelogram was in the first section that we did on vectors. So the area of this parallelogram is the magnitude of the cross product of those two vectors. And if you calculate this, I encourage you to do so, we will find that delta u and delta v are common factors of the two, so they can be factored out. And what you will get is that this is going to be equal to the magnitude of the partial of r with respect to u times cross product, vector cross product, r v. That's the partial of r with respect to v. So you take the partial of r with respect to u, cross product with, vector cross product with the partial of r with respect to v. You can take the magnitude of that times delta u delta v. That is, in fact, the area of this rectangle, which is approximately the area of this region. And again, we're seeing a picture that the region that we have is, whatever it is approximately this area of this parallelogram. And remember that the cross product is calculated in this way. And again, we were in the UV plane, so K is 0 for that. So if we were to expand this along the K, we would get this. This is the 2 by 2 determinant. And so we have this equality right here, where this is a 2 by 2 determinant. So when I take the magnitude, realize the magnitude of K is, the magnitude of this is going to be the absolute value of the magnitude of this determinant. So Finally, the determinant that arises this calculation is called the Jacobian of the transformation and is given a special notation, illustrated with this definition. The Jacobian of the transformation t, given by x equal g of uv and y equal h of uv, is given by this. This is a symbolism. So anytime you see the symbol, this is going to be the Jacobian, and it's going to be the determinant of this vector, xu, xv, yu, yv. And that's going to be given by this relationship, this one times this one, minus this one times this one. The Jacobian is named after Jacobi, and it was used by many people. But the important thing to realize from our derivation is that the small area is actually this. So the area in the xy plane is actually going to be the absolute value of the Jacobian. It is positive because it's an absolute value. The Jacobian itself could be negative, but it's the absolute value, delta u, delta v. So whenever we're trying to do an integral over here in UV space, we're doing that, but it changes to this. So what will happen is when we start doing the double integral as a Riemann sum, that delta A that we have is actually going to be this factor. So you see, if x is equal to g of uv and y is equal to h of uv, then we end up with this expression, the Riemann sum. And when we take the limit, as we will, that the double integral over s of, when we change variables, f of g h times the Jacobian, the absolute value of the Jacobian du dv, is in fact this double integral that we have here. Now this foregoing argument suggests the following theorem is true, and actually you get the major idea of the proofs. There's some epsilons and deltas that we could have added, and those things are given in some courses in advanced calculus. But anyway, here's the theorem that you want to remember then. Suppose that T is a C1 transformation whose Jacobian is non-zero, and that T maps a region S, there's the region S, in the UV plane onto a region R in the XY plane. Suppose that F is continuous on R, that is lowercase f, is continuous on R, and R and S are type 1 or type 2 plane regions. Suppose also that T is 1-to-1, that's the transform, except perhaps on the boundary. Then the double integral R of f of xy dA is the same number as the double integral over S, f of x, y, and then we have to insert the absolute value of the Jacobian, and this is du dv. So theorem 9 says we can change from an integral in x and y to an integral in u and v by expressing x and y in terms of u and v and writing dA equal the absolute value of the Jacobian du dv. We're going to do some calculations in the second part of this lecture, but for now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.